In this lesson, we're going to be talking about Gay-Lussac's law, along with combined gas law and Avogadro's principle. Okay, so let's get this started. Gay-Lussac's law is going to be very similar to the other ones, except this time we're going to be relating pressure and temperature. Okay, so this time volume is going to be held constant, and so we're going to look at temperature and pressure, and we are going to say that they are also directly proportional. Okay, meaning if one is increased, the other one is increased. And if you think about that, at least there's probably someone listening that has thrown an aerosol can into a fire, and you know what happens, because pressure increases as the temperature. Okay, so remember we said that the kinetic energy is related to temperature, and so what happens is as the temperature is increasing, the molecules are colliding more frequently, and they're hitting the walls more frequently, which is in turn causing an increase in pressure. And so we've been talking about these things being equal to a constant, and so pressure divided by temperature is equal to a constant, meaning if one goes up, the other one also goes up, so that they would always be equal to the same value. So that formula should start looking very familiar. Looks like some of the other ones. P1 over T1 is equal to P2 over T2. Okay? And then just like what we did with Charles's law, we're going to go ahead and cross multiply to get everything on the top. And so we would have P1 times T2 is equal to P2 times T1. So just like Charles's law, where you'd never have volume and temperature, the initial multiplied together, it's the same thing here. You're not going to have pressure and P1 and T1 multiplied. They're always going to be on opposite sides. Sorry about that. I had an interruption. So let's work a couple of equations. This is just an example of Gay-Lussac's law, why you shouldn't put aerosol cans in a fire. It's very dangerous because they will explode because they can't contain the pressure as the temperature increases. So let's work some problems. This one says, what is the pressure inside of a 2.5 liter can of deodorant that starts at 50 degrees Celsius and 1 atmosphere if the temperature is raised to 100 degrees? I have this 50 right here written in red because I found the typo after I sent it off to print, so it was too late. So make sure you make that change in your notes because it actually lists the volume again. Okay, so in this case, the volume's just going to be extra information because the volume's not changing. So we can just mark it out. We are not going to be using volume. So it's going to be asking for pressure. So it says, what is the pressure if it's starting at a different one? So we're going to be looking for P2 in this case. And then we're going to have our T1, okay? And remember what I told you, when you see your temperatures, go ahead and automatically change them to Kelvin. And so we would add 273 to that and get 323 K. And our first pressure, initial pressure, is 1.2 atmosphere. And then since we're raising the temperature, it's going to be T2, and that's going to be 373 K when we go ahead and convert it. Okay? So we have P1 times T2 is equal to P2 times T1. And we are solving for P2. So we're going to isolate P2. So T1 is going to go to the other side, and it'll go on the bottom in the opposite position. So it should be P1, T2 over T1. And if you're having trouble still understanding how I'm doing that, you might want to go back to the last lesson when I talked about how to rearrange that equation. Okay? So now it's plug and go. So we're going to plug in our numbers. We have 1.2 atmosphere for P1. This time we need T2, which is right here. So times 373 K. Divided by T1, which was 323 K. Sorry, 323 K. And our Kelvin temperatures cancel out. So when we get our answer, everything's in, we need two significant figures because that's the smallest one right there. So our answer would be 1.4 atmosphere. All right. Again, we can do that thing where we say, okay, our temperature increased, and since they're directly proportional, we would expect for our pressure to increase, and it did, so we were on the right track. In this one, it says, at what temperature will the can above have a pressure of 2.2 atmosphere? So this is a continuation on the previous problem. And so from the previous problem, we said that P1 was 1.2 atmosphere. Okay. And we said that this will be our P2, what they gave us. And then our T1 temperature, so that was because we're looking for T2 now, because it's saying, hey, at what temperature would it be above 2.2? So T1 from the above problem, we said was 323 K, or Kelvin. So again, P1 times T2 is equal to P2 times T1. We're solving for T2 this time. So T2 is going to be equal to P2 T1 over P1. Now we plug and go. So P2 is what they gave us in this problem, 2.2 atmosphere. Our T1 was 323 Kelvin. And we divide that by P1, which was from the original problem, 1.2 atmosphere. And when we get that, T2 is going to be equal to 592 Kelvin. Or if I wanted to convert it back into Celsius, I would subtract 273 and I would get 319 degrees Celsius. Let's do a double check. Okay, so our pressure increased, so we expect our temperature to increase. Sorry. And of course it did. It went from 50 degrees Celsius to 319. That's quite a bit of an increase, but we increased our pressure by a whole atmosphere, which is quite a bit. All right, that brings us to the combined gas law, and if you could guess by the names, that means we're going to combine the three gas law we've already talked about. So this law combines Boyle's and Charles, and it combines the Gay-Lussac law. So it combines all of those, and the formula looks like this. P1 V1 over T1 is equal to P2 V2 over T2. Or we can go ahead and cross multiply and learn it that way, and it'd be P1 V1 times T2 is equal to P2 V2 times T1. Okay, and honestly, between those three gas laws, this is really the only one you need to memorize between those first three, because if you look at this and we hold a parameter constant, we actually already have one of the other laws. Okay, for instance, and let's see if I can do this without messing it up. Let's try it this way. So for instance, if I said that I'm going to hold temperature constant, so I take out temperature of the equation because I'm holding it constant, then I'm left with Boyle's law. Okay. So then let's put temperature back in, and now let's say in the next equation I'm going to hold volume constant. So I take out volume, and now I'm left with Gay-Lussac's law. Let's put it back in, and then of course I can also say if I hold pressure constant, I take out pressure, and now I have Charles's law. And so that combined gas law takes care of all three of those laws. And so if you're reading a problem and you just use combined gas laws and they say something's held constant, or they just give you one parameter and they don't give you any changes, then just hold it constant and just use combined gas law. So let's work a problem. We have a 15-liter cylinder at 4.8 atmosphere. So we're going to have our first volume here. Pressure 1 here, and then 25 degrees is going to be, of course, 298 K when we add our conversion. It's heated to 75, so that's going to be T2, and that's going to be 348 when we convert it, and it's compressed to 17 atmosphere, so P2, and wants to know what is the new volume. So we're going to be looking for V2. So let's do our equation, P1 V1 times T2 is equal to P2 V2 times T1. And we're solving for V2. So when we isolate that, it's going to be P1 V1 T2 over P2 T1 because they go to the other side. Now we plug everything in. So solving for V2, and we get P1 is 4.8 atmosphere times 15 liters times T2 here, which is 348 K, and we're going to divide that by our P2, which was 17 atmosphere, and T1, which was 298 K. So atmospheres cancel, and so does the temperature. Now, let me caution you when you go to put this in the calculator, okay? So you are going to need to either use that N over D key, like on my calculator, or when you type this in down here, you're going to need to put divided by parentheses 17 times 298, close parentheses. Because if you do not do that, it will not come out of the calculator correct. Okay? So we plug that in, and we should get our volume. And of course, everything's in the smallest sig figs is 2. So we plug that in, and we would get 4.9 liters. Okay? So that would be our answer. Next one is 6.2 liters of gas. So that's going to be our volume, V1, at 723. That's going to be P1, and 294K, T1. And it's compressed to 2.2, so that's V2, and a pressure of 4,117. What is the new temperature? So we're going to be looking for T2, okay? We don't need to convert Kelvin because it's already in there, okay? So again, P1 V1 T2 equals P2 V2 T1. So this time we're solving for T2. So for when T2 is isolated, it's going to be P2 V2 times T1 over P1 V1. So now we just plug everything in. Pressure 2 was 4,117 millimeters of mercury. Volume 2 was 15, I'm looking at the previous problem, sorry, 2.2 liters. And then T1 was 294 Kelvin. Divide that by P1, which was 723 millimeters of mercury, times, I'm going to go ahead and take that out so you know to make sure you put parentheses around it, times 6.2 liters. Okay? Now I plug it in and do my math, multiply the top, divide by the bottom, and I get my second temperature is 594 Kelvin, or if I wanted to put it back into Celsius just to get an idea, it would be 321 degrees Celsius. Okay? Now, concerning temperature, if you're solving for temperature, if it specifically asks you for Celsius, then you have to put it back in Celsius. But if it doesn't ask, you can leave it in Kelvin. So you could have left it in this one right here because it's not specifically asking you. So if it doesn't specifically ask for Celsius, just leave it in Kelvin and make things easier. All right, one more law and then we're done. This one is Avogadro's principle, and it's going to be very similar to the other ones. This principle states that equal volumes of gases at the same temperature will contain equal number of molecules. So volume and number of molecules are directly related. And hopefully by now you've realized that the only two things that are not directly related are pressure and volume. They're indirectly, but everything else is going to be directly related. And so volume and number of moles, because we do number of moles as N equals number of moles. I don't know why they gave it a little n, but they did, is equal to that constant. So because of that, our formula looks like this. N2. And then, of course, we can go ahead and rearrange that and cross multiply, and we get this. So by now this little concept of these type of formulas should start looking familiar. All right, so let's do one example and then we are done with this lesson for today. Oh, that's just kind of a visual for you to see that I've got 4 different gases, all have different masses, but the same volume would represent the same number of particles. So if you want to take the time to count the particles, go ahead. Notice that some are molecules, like these, same number of molecules, same number of particles. That's why it's called, they're called particles, because they could be atoms or they could be molecules. But the same number of, same volume would have the same number. All right, this time we have if 2.3 moles, that's going to be our N1, occupies a gas at this volume, that's going to be V1. How many moles, that's what we're going to be looking for, are required or would be required to fill 126 liters, assuming that pressure and temperature are kept constant. Okay, so that's going to be V2. So let's go to this. V1 N2 equals V2 N1. We are solving for V2, so it should look like this when we isolate. V2 is equal to V1 N2 over N1. So let's plug everything in. So we have 73 liters for V1. We have N2, which is the higher number. So, oh my goodness, I'm so sorry. I totally was solving this wrong. Let's go back and start that again. We're not going to be solving for V2. Sorry, we are going to be solving for N2. I apologize. Okay, so N2 is going to be V2 N1 over V1. So now let's do it correctly. V2 is 126 liters times 2.30 moles, because that's N1, divided by V1, which was 73 liters. Okay, same thing, because they're directly proportional, we can see that volume increased, so we're going to expect that moles, or N, would also increase. So I multiply the top and divide by the bottom, and I need 2 significant figures because of this one right here. So I would get my answer, and it actually comes out to 3.97, but when I round that to 2 significant figures, I would get 4.0 moles. And that would be my answer. And that ends today's lesson.